Bene, allora, ripartiamo. Then first of all, organization of the next few weeks is basically holidays. So the partial exam, is the 2th of May. I'm sorry for the change. Oh, I said the 3rd, but that was not possible. So 2nd of May, I hope it's not a big change of plan for you. In the afternoon, 5:03. And the room is 5:03. It is in the old building, in the main area. Okay. So it will last probably 1.5 hours or maybe 2, I don't know. Exercise, numerical exercise on the first part of the course till, let's say, today. Included today. Today is the last lesson of the first part of the course, 6 weeks. Mainly ring resonator. So today we start and conclude the more formal part on ring resonator. The application of ring resonator, it will be the second part of the course, starting 7th, 8th of May, Monday, I don't know exactly when. Just a second. So the 8th, Monday 8th May, we started the second part of the course. So with the application of the ring resonator, then magneto-optic, isolator, circulator, Bragg grating, modulators, and indium phosphate, silicon photonics, and optical interconnect. This is the plan of the second part, starting from the 8th of May. In between is the longest stop. The 19th of April is Wednesday, right? It's the only day available in between. All the rest is holidays. Exercise section, just for you, right? Okay. You have to enter in the website and put your name for the registration to the exam from tomorrow. From tomorrow it will be available, so you have to register for this exam. Do not come just for fun, right? So if you come, this is a serious moment. It's an exam, so it's a formal moment, and you will be judged on your exercise and your exam. So then you can accept or not, and in June, July there will be the final examination, and if you decide to keep the result that you get here, it's an oral exam on only the second part of the course. Okay? If you decide not to keep this one, it will be an oral on the entire part of the on the entire course. Is clear the rule?
Could you put online after the exercise session some of the exercises in order to?
Sorry?
Could you put online after the exercise session some of exercises to solve as a practice? So.
No, basically are the exercise that we have done during the course. The 19
okay,
you have
so
an example. It's just,
so we will do based on the previous.
What about the 26th on Wednesday? 26th.
the 26th.
It's a Wednesday.
The 26th. I think it's holidays.
Okay, sorry.
It's holidays. Yes. 26 is holidays, and then the next week is there is no lesson. So
Okay.
I can do nothing. It's a long stop in the straight. So be serious on this one, and this will be your business card for the final examination. In any case, all right? Good. Okay, that's all. So we can go back to the ring resonator, right?
What is your opinion about students who don't take this midterm exam? Do you,
Have blacklist?
Nothing against the student. That
Do you have blacklist or something? No, yeah. Did you come to your midterm? No,
As I told you, this is a business card. So if you come and you realize that you are not really prepared, it's better not to participate, right? Don't make me correct empty pages, right? It's not serious. Okay. So now we go back to this fascinating object that is the ring resonator. It's really fascinating. It's really full of physics and possibility of exploitation and so it's basically a resonator, a cavity. The most classical resonator is the Fabry-Perot resonator. We use this Fabry-Perot that basically are two partially reflecting mirror. Usually the reflection is quite high, one in front of the other. So this is the path of the light, and you have these two mirrors, one in front of the other. And the light tends to bounce up and down these two mirrors. And the result, that is the transmitted light or the reflected light, depends on the characteristic of the resonator, so the length of the resonator, the material inside, the frequency, the wavelength, the polarization, so on. Right. So this is the most classical, I think that maybe the 50% or even more of the laser are based on Fabry-Perot resonance. Another implementation of the Fabry-Perot, so the light arrive, a part is reflected here, a part continue, a part is reflected and go back. So if you unfold this part of space, you basically have something like this. So the light arrives, the part go back, the part is coupled, this is a directional coupler, so started to travel in the ring, the part couple to the output and the part go back. And so once again, in this case, there is a light that continues to recirculate in this ring, and we have two ports, this one and this one that corresponded to the reflection. So the two are physically different, but the behavior, the transfer function is exactly the same. So this is called a ring resonator. And as we discussed yesterday, this is the realization, optical realization of this object that in digital signal processing language is an infinite impulse response filter. Okay? Now, how you implement the mirror, the reflector, and the directional coupler depends on the technology, depends if you are in free space, if you are in integrated optics, the material, etc. And here you see, as we discussed yesterday, a larger number of different structure, apparently very different one from each other. Why? I don't know. Sorry. So they seem very different, but all these are cavities, Fabry-Perot or ring resonator or a sphere. A sphere is just a ring resonator. Yesterday we discussed, we go through the story of a ring resonator. This is a very nice example of the first realization of ring resonator with some defect inside, and the first ring resonator in silicon, and a huge amount of application in many fields. Not only optical communication or telecommunication. This is a case of, this is an example of it seems similar to an AWG. It's a demultiplexer or router. We will go into the detail of this structure, and in optical interconnect, so you already seen this picture, and in the node, this crossing of the waveguide, there are nodes like this with plenty of ring resonators, and application as a sensor, as biosensor. Because they are particularly sensitive, we will see how sensitive, how much sensitive are with respect much more than Mach Zeta. Yesterday we concluded with this slide This is a very interesting device. You see here the ring resonator, and is totally suspended in air. There are just these four support, very thin support that do not perturb the light too much. So is suspended in air, coupled to the waveguide, the bus waveguide here, and below there is another one, so two rings coupled together and free to oscillate. They are very light, they are very small, very flexible because it's silicon, so they are able to move and resonate, mechanically resonate at hundreds gigahertz or hundreds megahertz or even gigahertz. So it's extremely fast. So you have a coupling in this kind of structure between mechanical effect and optical effect. And this was the start of an interesting field. What can I do? An interesting field that is optomechanic. So in some way join mechanical property of the material and the optical properties. And when we talk about optical properties, there are electrical properties also in between. The objects are very small, so can be really very fast, and you can combine and you go towards a multi-phase approach. So transfer function. Okay, let's calculate the transfer function of. Let's stop this blinking object. So the transfer function of the ring resonator or the Fabry period is basically the same. So okay, remember to register on the website. It's not dangerous, it's just for me to have the list of the people, so the Excel file ready, and not type again your name. That's all. So, let's consider this structure. Two-directional coupler connected in this way. So we have this port, we call it input, this port, we call it the through, we call it this drop, and I don't write the fourth one, but you can imagine the name of the fourth one. I can write it. At the moment we do not use it, but it's like the yes. So we assume the length of the ring equal to LR, the effective index of the waveguide, the group index of the waveguide, the attenuation of the waveguide, as usually, as you know. So you know the characteristic of the waveguide. The directional coupler, let's use the same symbol of the note and of the other slide that you have available. We call this in the directional coupler R, and the coupling coefficient is JT minus JT. First coupler, second coupler, so we call it R1 and T1, and we have R2 and T2 on the other side. Okay. Basically, T to the square is equal to the coupling coefficient, big K that we have used before. I change a little bit the notation because it's more common. Okay? So we consider synchronous coupler because it's easier. Synchronous coupler, the R and T small letters, so means the field. T is the field coupling coefficient, and R is the amplitude, complex amplitude of the field that continue in this direction. Okay, now we want to calculate the transfer function. So there are, let's say, several ways to calculate the transfer function. I want to show you, well, one possibility is this one. So we calculate the transfer function between the input and the through port. So this is in through port, HT. And we calculate as we have done for the Mach-Zehnder. In the Mach-Zehnder, we had a direct path and a delayed path. So we say is 1 plus the contribution of the other one that was this one. You remember? That was the Mach-Zehnder. So we can do the same here. So let's try to do the same here. So the light arrive and we have a contribution equal to R1. Is the part of the light that does not couple to the ring, go straight, arrive to the end, so is R1. I neglected the physical length of this waveguide, but this is a common phase term that stays in front of everything, so it does not play a big role. Okay, this is the first contribution. Then we have the light that is coupled to the ring. So we have to write plus minus JT1, the amplitude of the light coupled here. The light go around the ring and go back to the coupler. So we have to add A minus J beta LR, so the phase term that go around, multiplied by what? If there are some losses, let's call alpha L equal to gamma. Okay, so let's call gamma the round trip losses. Gamma is called round trip losses, gamma. Then we have some light that couple in this direction toward this port and the part that continue. So we have to multiply by R2, that is the light that go up. And then when you go back to the directional coupler, you couple back to the bus and you exit. So you have to multiply by minus JT1 once again. Okay? It's a long way, but we went through the entire ring, we couple back and we exit. Okay?
What is the difference between gamma and the phase shift before? This is the losses of the ground, and the previous one.
Gamma is the round trip losses.
And the previous one, J beta and
is the phase term. The phase accumulated by the ring. Okay. Then this is the contribution to the output of the light that went through the ring around and out. But when you come back to the coupler, a part is coupled back to the bus, and the part continue and go around again and go back to the ring. So I need meters of the board to add all the other components. And well, it's an infinite number of terms, because this is an infinite impulse response filter. It's not a finite impulse response filter. With Magzender, we had just two terms, the direct one and the delayed one. But in this case, it's an infinite number. So we have to add what? Basically, this part multiplied by R1 multiplied by another round trip. So once again, multiply by this term, plus etc., etc., etc. So you have to continue. So it is an infinite series that you can write, hopefully, in a closed form formula. And if you rearrange this infinite series, is quite boring, but not difficult to do. You get this expression. No, sorry. This is the transfer function at the through port of a ring resonator with two different directional coupler, so the most general case. And you can do the same with the drop port. So calculate all the contribution, the infinite contribution that you have, or if you are smart enough, you can do it just 1 minus HT. And what you get is minus T1, T2, square root of gamma, half the wavelength, and the denominator is exactly the same as before. So this is the transfer function input to through port, and this is the transfer function input to drop port. Okay.
I didn't get why you would add to the interest in the second term.
Sorry, miss completely.
Yeah, I didn't get why you would add R2 in the second term. What does R2 stand for?
When you arrive here up to the second coupler, okay, you arrive here, a part is coupled to the output port, and the part of the light continues straight. So that coupler has this transfer function, minus JT2 R2, exactly as the other one, but 2 instead of 1.
Sorry for that. At port we have the same, but R1 and R2
For the
at port. We have the same transfer function, but the R1 and R2 are exchanged with the places.
yes, yes. At that point, this one is the true and this one is the wrong. Sure. Yes. Fine? Clear? No? Sorry?
You don't have to put minus JT2 in this sequence.
Where?
minus JT2.
But where?
We don't have to put it.
Here? No, this is the true port. So you never cross this. You always stay inside. So you see the bar port of this coupler. This one. You never cross. JT2 appear only if you go to the drop port. Okay, there is another way to calculate the transfer function, similar to what we have done for the Mach-Zehnder. If you think to the ring like a combination of building blocks that you know quite well, we can think to this matrix. So we have 2 port here, 2 port here. Maybe it's okay. Then we have the central part. These are 2 waveguide uncoupled. And then there is a matrix that describes this directional coupling. So another way is to multiply the 3 transmission matrix of the directional coupler, the 2 uncoupled waveguide, and the other directional coupler. So this is another way to calculate the transfer function.
So in case in true, the last, the upper matrix doesn't work. The upper matrix, the upper
Yes.
implies the using of a minus J2, right?
Yes.
Yes, and in this case we only add this, right?
I don't really understand the question, but the blocks that I draw are described by a matrix, 2 by 2 matrix, as we have done for the Mach-Zehnder. And then you have to multiply this 2 by 2 matrix together to get a 2 by 2 matrix figure of the entire ring. And this matrix relate these 2 ports to this 2 port. Then you can always change the matrix, invert the matrix as you like, depending if you want the output as function or the input or vice versa, or etc.
We relate the inputs to drops.
No, in this way you relate this 2 port to this 2 port. But you can manipulate the matrix as you like. So this is another way. This way is more complicated, but I think give you an idea of what happens physically inside the ring. So light enter, go around, the part go out, the other continue, etc. And it's very clear from this approach that the other port remain isolated. There is no light that go out from the other port. Because you can go through the ring and reach the through port, or if you enter and you started to go around, you go to the drop order, there is nothing that changes the direction of the light to the add port. So the add port remains isolated.
Always one direction. Always one direction that's the same. So
Yes, if there are no defect, discontinuity, reflection inside the ring. Yeah. Okay, now we can have a look to this expression and see and try to read the two expressions. So, first of all, we start from the through port, for example. The through port, we see that if, well, it depends on the wavelength. The wavelength is inside beta, so there is dependence on the wavelength, as we expect. So, this dependence is related once again to the phase accumulated in the ring. Beta phase. So is 2 pi divided by lambda, the effective index of the ring, multiplied by the length of the ring. So from here you can say that if this condition is equal to 2n pi, with n an integer number, the phase of the light that go back after a round trip is exactly equal to the phase of the light that enter in the ring. Equal in the sense of the phase. So apart 2n pi multiple. So in this condition, we say that the ring is in resonance. Because the light that go around go back and add to the light that arrives. So there is a build-up of the light inside of the ring. I repeat. You want?
Just the last time.
Yeah. The light that go around go back to the coupler with the same phase of the light that arrives. So it add in phase, and so there is a build-up of the field inside the ring. So the light go around once again and arrive to the coupler with the same phase of the new light that arrives. And then continue to build up. Continue to increase the intensity. Not infinitely, hopefully. And this is called the resonance. If this is 2n pi plus pi, the light that go back is in antiphase with the light that arrives. So, reduce the intensity of the light inside the ring, and try to cancel, and we say that is anti-resonance. Okay? Good. Resonance and resonance. Has to say no. Okay, so the resonance wavelength is 2 pi disappear. Effective index, the length of the ring divided by an integer number. So basically the resonance is when you have a finite number, a right number, integer number of wavelength in the cavity. Okay. So the periodicity. The periodicity is lambda n minus lambda n minus 1. And how is called this periodicity? Right, good. And if you play, remember, this is wrong because the FSR is in frequency, is not lambda. So is the difference between the two, and is if you play a little bit with the formula, you get C divide, easy to find speed of light divided by the length of the ring, the group length of the ring.
Each time I have a feedback, will it change my lambda or
No.
because
The device is linear. There is no generation of new frequency. So the lambda does not change. And you go back.
what does lambda N mean here?
Is the wavelength of resonance, and at this resonant wavelength you have n lambda inside the ring. So the length, the optical length of the ring is an integer number of lambda equal to n. If you change the frequency, you change the wavelength, start to decrease the resonance, you arrive to the anti-resonance, and then you start again to resonate, and you arrive to the next resonance, and then go down again. Then we will plot this one. But first I want to discuss the expression, and then we give a look to the plot.
So we find lambda n as the wavelength at which you have resonance.
Yes.
And we have an integer number of
Yes. As for the Marzender, in Marzender we do not call a resonance because it's not a resonance, but it's the condition where you have the cross or the bar equal to 1.
Supposing to have that resonance, will resonance go on building up to infinite, or will it separate?
No, not to infinite. We will see. We will see. At some point it stops. Stop because you continue to increase, so the light that go back add to the input one. So when there is a given relation between the two, it's separated. At this in this condition, the exponent is equal to 1. So the HT at this wavelength, HT is equal to R1 minus gamma R2 divide this term at resonance. So if R1 is equal to gamma R2, what's happened? The transfer function in the through port becomes 0. The transfer function to the through port becomes 0. So we have a notch in the transmission in the through port. At the resonance, nothing exits from the through port, and if you calculate this one, you get immediately that everything exits from the drop port. So at the resonance, the light arrives, start to couple to the ring. You have an intensity that build up until you can send completely the light that go out from here, and all the light is magically coupled to the output port and go out from here. If this condition is satisfied. So typically, if you have two equal directional coupler, so R1 is equal to R2, and you have no losses in the ring, in the ideal case, this is the simplest case where the line really is trapped in the ring and go out from the top port, and nothing can be zero. Yes. After a certain time, yes. When we go through the group A of the ring, and we will see also this aspect. Basically, this one become 1 because r to the square plus t square is equal to 1. You have no losses inside the directional coupler. So if you substitute this one, it becomes j, this one becomes 1, you have no losses. So if you substitute that one inside here, you get immediately that is equal to 1.
When we go from directly to the soup,
When we
how we go, now we go from into, when we satisfy this condition. If I want to go to cross,
no, we switch to anti-resonance.
JR2 is equal to 0.
So these are the points on the matches in the resonator.
Is the
Peak points when it goes down.
the notch?
The notches. This is the condition when all gets out of
At resonance, in the through port, you don't have light, and the transfer function go down. We will see then the plot. I want to discuss the formula before, then I show you the plot. Is a notch, and then this condition is the ideal condition in which the attenuation of the VGI is 0. Alpha equal to 0 means gamma equal to 1. So the round trip is 1. This condition, no. This condition tells you that the first coupler must match the second one multiplied by the loss of the upper part, let's say.
this losses, the path losses, doesn't accumulate with the phase, the beta LR. This losses, the path losses, alpha LR.
The losses.
Yeah, it doesn't accumulate or change the phase while
The losses does not change the phase. The losses change the amplitude. There is some misleading term. Gamma is usually called round trip losses. No? Because it is alpha e to the alpha LR. But it's not really loss, it's a transmission. Because if the losses are 0, gamma is not 0, it's equal to 1. But everyone call it gamma round trip losses. And so just keep in mind that sometimes the terminology is not exactly formally correct. So I prefer to use the language of everyone and say that gamma is the round trip transmission, if you want. If you have alpha, then gamma become smaller than 1. 0.99, 0.95, 0.5, and depends.
Prof, in this condition, we say that the throughput is 0.
Throughput is 0.
Yeah, so will there be any output light? through the through
Any
light through the output? This one.
this one?
Yeah.
No, if this condition is satisfied.
But when you define R1, how do you define R1? R1 you define that amount of like amplitude that goes through the R1.
That is,
So you define it as a light, right?
is the complex amplitude, the transmission in the coupler. Yes,
In general, in the coupler.
in the coupler. It's only for the coupler. Only for the coupler. So if you enter from here, you get out from here and from here. The amplitude here is called R1, and the amplitude
So this is
here
the light.
is called
R1 is the
minus
light.
JT1.
R1 is the light.
It's not the light, it's the transmission.
Exactly.
It's the amplitude.
So, but when you say that R1 is something equal to R2, so there is some amount of this wave, which gives us throughput is equal to 0. How is it related? Are you getting the question?
This is a directional coupler,
Yes.
and that is a ring. So it's different.
But we are satisfying that condition. R1 is equal to gamma times R2.
If you don't have attenuation, gamma is equal to 1, so that condition means that these two directional couplers are identical. If you have gamma, it means that this directional coupler is not equal to this one, but are related through the attenuation of the Volga. So if this condition is satisfied, no light exited from the through port.
Then I am confusing with the definition of R1. Can you just repeat it? Maybe
R1 is the sin square of CL. Well, it's a sin. Field coupling coefficient, the length of the coupler. Okay, so the resonant frequency, the anti-resonant frequency, and the free spectral range. In anti-resonance, what's happened? This become J, so you see that this is never equal to 1. Formally, you never reach 1 condition. As this one never reaches 0. You never have a 0 here. So you have a pole, is a transfer function with a pole, but not with a 0. The 0 is in the origin, to use a digital signal processing language. You see, this one never reaches 0. So you don't have a 0 in the transmission.
R squared plus E squared. It was for resonance in the case of the
No, this is for the directional coupler. It means that we have no losses in the directional coupler. It's valid for every frequency. Okay. What else about the transfer function? Let's say, okay, like this, and now we can have a look to okay. So go back to the slide. Transfer function, you can download the slide from the website. And ring resonator and Fabry-Perot are exactly the same from the transfer function point of view. So the reflection, so this port, the drop port is the transmission of the Fabry-Perot, and the through port is basically the reflection. You have one pole and one zero, as we discussed. So the transfer function is this one. These are the formula that I derived before on the border, and input through drop port. So the through port is this blue line. So the through is always very close to 1. It means that the light that enter from the input basically go to the through, almost for every frequency, except near the resonant frequency, where it drops down very quickly and gets to 0 if this condition is verified. Otherwise, go down to something that depends how far we are from that condition. The drop transfer function, that is this one, this is the field transfer function, and here you have the intensity transfer function, so the modulus of these two is the red curve. So you see here the resonance, and then go down, stay down until the next resonance, and then continue periodically in spectrum, in frequency. The resonance conditions are this, as we wrote, and the free spectral range is given by the same, always the same. So you see that the drop go down, but you never have a 0. You never have a notch, because in the transfer function there is no a 0 here. We have a 0 in the through, but not in the drop, while we have a pole, and so we have a resonance. And the resonance goes up to 1, that is to the top, if there are no losses. Otherwise, if there are losses, it remains a little bit below.
So that we can have a perfect transmission in drop, so we have no transmission through when we are in a resonance wavelength.
Yes.
But when we are not in the resonant wavelengths, we will always have a drop transmission.
Yes.
Even low, but we always have. So
it never gets to 0. This expression never gets to 0.
So all the power will not go to true.
True, but something go to the drop port always. But we are engineers, so we know that 0 has a different meaning for us. Okay. I want to introduce now a couple of extremely important parameters. Can cancel. I just noticed that there is an error here, and n should be nef LR divided by n. So n should be on the other side. I just discovered it's years that I use this slide and never noticed. Okay, something to correct. I can cancel, I think, everything here. I want to introduce a very important parameter. Well, first of all, the bandwidth. bandwidth is defined usually at 3 dB, but you can define the other intensity. So give you the spectral width of this notch. The concept of bandwidth of a resonance circuit is common and has the same meaning of an electrical circuit resonance or mechanical resonance or any other kind of resonance. So the ratio between the free spectral range and the bandwidth is called the F finesse. Is a French term because Perrault and Fabry were two French, and people use this term. So this gives you the selectivity of the filter. Free spectral range is the periodicity, B is the bandwidth, so tell you how large is the filter with respect to the periodicity. So this is an interesting point, and a very big difference with respect to the Mach-Zehnder. In the Mach-Zehnder, you have a sinusoidal transfer function. You cannot change it. While the bandwidth is always 1/2 of the free spectral range. While in a ring resonator, you can decide the bandwidth. And the bandwidth depends on, we will see, other parameters. Another important parameter that everyone uses, except me, is the Q factor. And the Q factor is the resonant frequency divided by the bandwidth. Now, you probably found that the Q factor in electrical resonator, LC, I guess. It tell you is the quality factor of the resonator.
Professor, sorry, is F0 what is it?
Is the resonance frequency. Yeah.
It's the set of
What? The resonant frequency that you are using, the one that you are considering. So before we call it lambda n, so now it's f n. If you play a little bit with the formula, you have let me see if I have a slide with no, I wrote it here. The finesse or the bandwidth can be expressed as a function of the coupling coefficient, and the expression is of the bandwidth is free spectral range divided by pi multiplied by coupling coefficient divided by 1 minus coupling coefficient. So in our terms, k is equal to t to the square. So the coupling coefficient of the directional coupler that you use in the ring. So big K is the power coupling coefficient. T is the field coupling coefficient. Okay? So the finesse is the free spectral range divided by the bandwidth, so is pi multiplied by 1 minus big K and divided by big K. So the directional coupler has a very important role. If you the directional coupler tell you how much is the bandwidth of your filter, while the dimension of the ring, I wrote it again, the dimension of the ring, optical dimension of the ring, give you the periodicity. So the dimension, only the periodicity, the coupling coefficient, only the finesse, and both the bandwidth. So this is a relation between these two. So if you change the coupling coefficient, you can change the shape of the filter. We don't have a plot of this, strange. I don't have a plot, okay, no problem. Okay. So this is the just a part of the previous transfer function. So this is an entire spectral range, and now we just zoom on this part, and we get this. So once again, this is the drop transfer function over one free spectral range. So this is anti-resonance, resonance, anti-resonance, and this is the notch that you have on the through port at resonance. If you change the coupling coefficient, you change the bandwidth, and so you change the extinction ratio, the isolation out of band. It becomes larger or smaller. I'm sorry that I don't have a plot. I can easily find it. Maybe. Okay. From the transfer function, from these two, okay, from these two, you can calculate the phase of the transfer function. This is the intensity. From these two, you can calculate the phase, and the phase is something that is not linear. So typically, it's something like this. This is the frequency, this is the phase. So it's not linear like in a Mach-Zehnder, but the shape is highly nonlinear and depends on the coupling coefficient. So for a very small coupling coefficient, you have a strong jump around the resonance of the phase. So basically the input to output phase does not change much. At the resonance you have a big jump, and then once again. And the jump is 2 pi. It's not really important the phase, but what is important is the group delay. If you do the derivative of the phase, you get the group delay. So the group delay of the true and drop port, this is the intensity, this is the group delay, is something like this. So near the resonance, the delay between input and output started to increase, reach a maximum, and then go down again. In resonance is where the light is trapped for a long time. So it entering the ring, started to go around, recirculate, and then go up. So it's, if you look at this, this is the group delay divided by the round trip time. So the time that the light needed to go through the ring. So it is 4 in this case for a coupling coefficient, power coupling coefficient equal to 0.2 is 4. It means that the average number of round trip that the light do before exit from the drop port is 4. So the group delay is 4. The normalized group delay is 4. It means that the light enter, go through 4 times, and then exit. And physical people call this photon lifetime. I call it group delay. That's all. Look at so this is the group delay of the drop port. Look at the group delay of the through port, is the dashed one. You follow the other one, and then here go down to negative value, go up, and once again. The group delay of the through port lose the meaning of delay of the information, delay of the energy, delay of the signal, because of this very low intensity of the output. You have a very strong variation in the intensity, and as a consequence, a strong variation of the phase, and in this case, very low or even negative value of the group delay. Nothing strange, does not mean that the light appears at the output before the input, but just that the meaning of the group delay is no more the delay of the information, energy, power of the
The other curve in the group delay, the dotted curve is a group delay.
Yes.
Is in transmission.
Is the group delay at the through port.
It means when each time I rotate 4 times. Because,
yes.
So what does it mean exactly when there is notch in the through?
This notch or this notch?
In the group delay.
In the group delay, it means that the signal is strongly attenuated and distorted, basically. Strongly distorted. The second derivative of the group delay is the chromatic dispersion. So tell you, how much time of delay between the spectral component of the spectrum of the signal. And this, if you do the second derivative of this, is huge. It means that the shape of the signal is completely destroyed, is completely changed. Why I say that it is very important the finesse, and I not use the Q factor, but I prefer to use the finesse. The finesse is extremely important because it's related to the selectivity of the filter. So, tell you how critical, how difficult is the filter to do. So, most of the parameter of the filter depends on the finesse. So, if T is the round trip time of the ring, the group delay at resonance of the filter is more or less equal to finesse time the round trip. If the attenuation of the waveguide inside the ring or gamma, if this is the round trip attenuation, the insertion loss of the ring, so the losses at the drop port, are enhanced once again by a factor f. Enhanced by f, don't multiply gamma by f. Gamma is equal, let's say, is 1 minus gamma multiplied by f is the insertion loss. And everything is in some way enhanced by the physics. The intensity inside the ring at resonance is finesse time the intensity of the input.